Welcome back to Astronomy 405. We are picking up with erosive processes. So we're going to look at some of the sampling of erosive features and talk a little bit about what causes them. So grouped in kind of this process is what's called mass wasting. Let's start there because mass wasting can happen everywhere. Mass wasting is simply the fact that loose material flows downhill because of gravity, and since everything has gravity, mass wasting happens everywhere. Now you have to break apart the material to some extent, but you can pretty easily do that with either other erosive processes or even things like impacts. Small impacts on airless bodies can break apart material and form kind of a powdery regolith. Which then can undergo mass wasting. So here's some examples. We have one on the top from Earth, where we have wind and water to break apart rock and ice and snow and all those fun things. But we can have it on the moon. You can see a crater rim of Dawes Crater on the moon showing mass wasting. So this is one of the few erosive processes that happens everywhere. So what is erosion? Erosion is the breakdown and shifting of rock to either erase old features or make new ones. Mass wasting is a kind of erosion, and it happens everywhere, but if you add an atmosphere, you have more options for erosion. You don't have to rely on cratering to break apart the rock. In fact, adding the atmosphere means that the micrometeorites that break apart lunar rock don't make it to the atmosphere at orbital velocity, but you have plenty of other things that can do it, such as wind, fluid, in this case, water on Earth, or ice. So let's look at the wind-based processes first. We call them aeolian processes. So let's consider where these could occur. We need a solid surface, so that rules out the giant planets, and we need an atmosphere. So Mercury, of the terrestrial planets, Mercury is just straight out. It has no atmosphere. It has no wind. The other three terrestrial planets all have atmospheres, so they can have wind, they can have aeolian processes. Saturn's moon Titan is also in this category. A few of the lighter objects, Triton and Pluto, have atmospheres, but they're pretty thin, so aeolian processes are not a big deal. Mars has aeolian processes, but the wind is not as effective as it is on Earth. While Mars has lots of wind, the winds go very fast, can pick up sediment and carry them along, for Mars has those global dust storms. The air is thin, so it's hard for the wind to carry much stuff. So wind is a little less effective on Mars. On the other hand, if you don't have that many other processes to compete with them, they do a pretty good job. And a lot of what we see on Mars is sculpted by wind. So Venus also has aeolian processes, but it's got kind of the opposite problem as Mars. Mars has lots of wind, but not much air. Venus has lots of air, but the very slow rotation doesn't create strong winds, at least not near the surface. Venus's upper atmosphere is an entirely different matter there. Titan is in the same boat as Venus. Its air is reasonably thick. It's only a little thicker than Earth's. Because it spins slowly, it's not driving those wind speeds near the surface. So while both of them have aeolian processes, they're not as strong as the ones on Earth. Earth is kind of, like many things, Earth is in the Goldilocks zone. It's got stronger winds than Venus and Titan. It's got more air than Mars. So it ends up having a lot of wind-based erosion. Now, the only reason we don't notice it as much is because Earth also has a lot of water-based erosion. So we tend to see the wind-based erosion features a lot more in very dry regions like deserts or Antarctica, which is also a desert. So here are some pictures of things that you can do with wind. Wind can carve rocks out, just like water can, but you can also accumulate sediment in patterns. So this is a view from above on the left of a dune field on Mars Vallis. These are what are called Barken dunes. They're very characteristically shaped. They kind of have that Star Trek logo look. And this is how sediments, sand or dust or small pebbles, accumulate on a surface and move around. These dunes actually slowly move. They also tell us something about the wind patterns. And there are different structures of dunes on and ripples on planets depending on what the winds habitually do. We can actually learn a lot about the regular wind patterns. We can see this on Venus and Titan as well. We don't have the beautiful, high-resolution surface pictures, but we have radar. And one of the cool things is because these things these dune fields and ripple fields align with the wind, they tend to scatter radar in a very characteristic way, in a very directional way. So we can easily pick them out on Venus and Titan. So what is a dune doing? So when the wind hits a bunch of sediment, the really fine stuff basically just gets launched in the air and it kind of just floats there. It's, subject to gravity, but the battering from air molecules means it doesn't come down very quickly, so it's just gonna eventually settle out, but not in any characteristic way. The big stuff that the wind can move at all just kind of creeps across the surface. The wind can't really lift it up, but it can push it along. And the middle stuff tends to travel the surface in jumps. We call it saltation. This helps form the dune. End up building a slow slope and then a sharp drop of the slip. You can see that kind of here. Now, one of the cool things is that dunes that are active actually do move, and we can track this on Earth and Mars. In fact, from Mars, we can do it from orbit, just basically slowly watching dunes slowly move. But what can happen is dunes can also be, the grains in the dunes can be cemented together. If you get water in it, the water might carry dissolved minerals, or you can just try to compact it. And then you have a dune that's fossilized, that's frozen. It's not moving anymore because it's now kind of a dune-shaped clump of stuff. And this is part of how you go from sand to sandstone. And we can even see the structures of dunes in rocks on Mars. Tell that there's some rocks formed as a dune, they then became rock. All right, so the other class of erosion is fluvial, fluid-based. On Earth and Mars, that meant water. On Titan, that means liquid methane and ethane. On Earth, this is by far the dominant surface process. You have some lovely pictures of stuff on Earth carved by fluvial erosion. That's why, generally speaking, we only see the wind-based erosion, the aeolian erosion, in very dry places, and we only see relatively recent formations or very large formations of volcanic and tectonic and impact events. Basically, Earth is chronically sculpted by water. It's by far the dominant influence on our surface. But it's not universal to Earth. Mars does not currently have any water, but we see the effects of past fluvial erosion on Mars. If you look here, we're looking not just at the water, but what the water is doing. On the picture on the left on Earth, the water has carved through a channel in the rock. We get canyon systems, and even a river will kind of reinforce its bed and occasionally carve new beds. We can see the remains of flooding by basically all the sediment, all the fine stuff that the water's moved. So we can see that on Mars, and it helps if the sediment, again, becomes lithified. It goes from sediment to sedimentary rock. Picture on the left is an Eberswald crater on Mars. We see this occasionally at craters. We'll see carved channels that presumably once carried water. They'll enter a crater and they'll form a fan shape. And on Earth, what this would tell us was that this is a river delta. When the river gets to a lake or a sea, it slows down and it dumps all its sediment. So on Mars, similarly, the same thing happened, and then the sediment cements itself together. It's a different sizes and possibly different composition than the rock or than the sediment that was already in the crater at the bottom of the lake, and so we can spot it. Also see the channels themselves. This is a picture from Antoniadi crater, and you can see that on Mars, and then we can see that it's carved out channel networks And this particular form, the way you have all those branching channels, it's called dendritic, a dendritic channel network. And basically, this is the sort of thing you get with precipitation, with rain or snow. You know, you get rain and snow fall on the ground. It slowly kind of accumulates into little rivulets. Those grow into streams, which grow into rivers, which, you know, flow down towards the sea. So this might have told us that past Mars, and this is some of the oldest terrain on Mars based on the craters, which we'll talk about in the crater video, tells us that past Mars might have occasionally had rain or snow, you know, and those carved these river valleys. And we do only see this in the very oldest rocks on Mars. We see some other fluvial features, but they all appear to be carved via basically large catastrophic events like floods. I don't have a slide for it, but we can also see lots of this on Titan. Titan is full of both dry and filled river valleys and lakes and all those fun things. It's hard to show you this because it's all full of the fluid that's still carving it down. Mars is easier to see the effect on the rock because the water's not there anymore. Ices can do this at higher temperatures. On Titan and the outer solar system, ice is pretty much a rock. It is nice and solid. Does not flow. But at warmer temperatures on Earth and Mars, and I'm using warmer as compared to the outer solar system, so relatively warmer. Ice is a little softer. It flows more easily. It's much slower than water, but it can still carve out channels. This is a ice-carved valley in the Himalayas on the left, and there is a glacier carving out its surroundings on the right on Mars. Now, one of the things about Earth and Mars, and presumably Titan once we get a better look at it, is that usually, again, you have both wind and water. Earth is more water dominated, Mars tends to be more wind dominated, but both are usually playing a role. You can't separate them out. And you can't separate them out even when you're not even looking for erosion. You're looking at like volcanoes. So when geologists study these surfaces, they have to consider both. Could this be wind? Could this be water? Could this be both? What role do both play? So today we talked about previous lectures in the series covered tectonics and volcanism. And then we talked about erosion, which features the breaking down of rock that removes features and creates new ones like sand dunes and deltas by building up that sediment and eventually it lithifying. So then the following lesson will be about cratering, but I already posted that one.